January 15, 1943. The North Atlantic, southwest of Iceland. The air temperature hovered near freezing, but the sea was the real executioner. Sub-Lieutenant Peter O'Malley, a radio operator aboard the British destroyer HMS Catastock, felt the icy spray lash his face as the destroyer plunged through the mountainous gray waves. Above the roar of the wind and the shudder of the ship's hull, the active sonar pinged with relentless, anxious regularity. The convoy they escorted, designated SC-18, was already a slaughterhouse. German U-boat operating in deadly wolf packs had torn through the merchant ships over the last 48 hours. The sea was littered with oil slicks, debris, and the tragic remnants of ships that had gone down in seconds. O'Malley watched a distress rocket flare in the distance, followed by the sickening, muffled thump of a torpedo strike. He knew the grim statistics better than anyone. If you were thrown into this water, the vast, deep, hostile North Atlantic, you had less than 5 minutes of functional consciousness before the paralyzing cold set in. Within 15 minutes, the average man succumbed to hypothermia, dying not from drowning, but from the brutal extraction of heat from his body. The water temperature here averaged 2 degrees Celsius. It was a liquid graveyard, a place where rescue was often too late, even if it arrived within the hour. The U-boat didn't just sink ships. They used the terrifying cold as their most reliable auxiliary weapon. The psychological toll on the sailors was immense. They knew that hitting the water meant certain death. Yet thousands of miles away from this cold immediate threat, in the quiet academic calm of a Canadian university, an answer to the U-boat's deadliest weapon was inadvertently being born. This solution was found not by a naval engineer or weapons designer, but by a frustrated physics professor wrestling with a completely different problem. Dr. Clooney McPhersonin, a professor at McGill University in Montreal and a researcher for the Canadian Department of National Defence, was tasked with designing a flight suit. The goal was to protect Allied airmen who might bail out over the frigid English Channel or North Sea. The common wisdom was simple: to keep dry. You must be protected by a completely watertight seal. McPhersonin designed a complex multi-layered suit heavily insulated and intended to be fully sealed at the neck, wrists, and ankles. It was the ultimate dry suit concept. The initial tests, however, were an embarrassing failure. The seals inevitably leaked. Water seeped in, making the suit heavy, clumsy, and cold. The professor's initial work was headed straight for the scrap heap of discarded wartime inventions. One frigid afternoon, while observing a drenched test volunteer emerging from the cold testing tank, McPhersonin noted something unexpected. The small amount of water that had inevitably leaked into the suit, trapped against the skin by the inner lining, was surprisingly warmed by the subject's own body heat. While the volunteer was soaked, he was not instantly paralyzed. The light bulb moment was profound and counterintuitive. The goal wasn't to keep the water out entirely, which was technologically impossible with 1940s rubber seals. The goal was to control the water that leaked in, trapping a thin layer of it so the body could warm it up and insulate itself from the crushing cold of the surrounding ocean. McPhersonin had quite accidentally discovered the fundamental principle of the wetsuit. His failed flight suit designed to be dry had revealed the secret to surviving while wet. This accidental discovery, made thousands of miles from the nearest U-boat, was about to become the single most effective life-saving device in the entire Battle of the Atlantic. The Canadian professor immediately pivoted his research, focusing on perfecting this new, revolutionary concept of controlled wetness. Mid-1943, Naval Research Laboratories, Dartmouth, Nova Scotia, Canada. Dr. McPhersonin's research shifted from McGill to the specialized naval testing facilities on the East Coast where the cold, unforgiving waters of the North Atlantic were readily accessible. He was now fully immersed in developing the concept he called the immersion suit. The traditional wisdom championed by British and American designers continued to focus on thick, fully sealed rubber dry suits, expensive, cumbersome, and prone to catastrophic failure at the seals. McPhersonin championed the counterintuitive. His central team, which included naval engineers and textile experts, worked on creating a practical prototype. They needed a material that was both insulating and flexible, capable of retaining the critical thin layer of body-warmed water. They experimented with tightly woven wool and special linings, layering fabrics in a way that permitted a slight water ingress, but severely restricted the circulation of that water, thereby minimizing heat loss through convection. The resulting garment was a bulky, often ugly, but revolutionary piece of equipment. It was dubbed the Grumble suit by the Canadian sailors, partly because of the complaints about its bulk, and partly because of the grumbling sound the fabric made when moved. Crucially, the suit was not fully watertight. It was designed to be damp. It was the scientific embodiment of McPherson's accidental discovery. The testing protocols were brutal and entirely necessary. Volunteer sailors and researchers were submerged in tanks of near-freezing water, monitored closely by physicians for signs of hypothermia. The control group, wearing standard naval uniform or early dry suit prototypes, consistently failed within the predictable 5 to 15-minute window before their core temperatures dropped to life-threatening levels. But the sailors wearing the Grumble suit exhibited survival times that were to the conservative naval doctors simply impossible, where the standard sailor would be shivering violently and entering the final stages of physical collapse within minutes. The Grumble suit wearer remained conscious, relatively composed, and most importantly maintained a stable core temperature for hours. A test report from late 1943 detailed an experiment where a volunteer in the suit spent 6 hours in water chilled to 5 degrees Celsius, 41 degrees Fahrenheit, and emerged conscious and able to perform fine motor tasks. The same exposure without the suit would have been fatal within an hour. The Canadian Invention had achieved a monumental feat. It had extended the average sailor's life expectancy in the North Atlantic by a factor of 10 or more. The secret was the trapped self-heated water layer. The suit's dense wool layers were designed to quickly soak up the initial small amount of cold water that leaked in, but then hold it immobile against the body's own metabolism. The internal furnace would heat this thin layer, creating a thermal barrier between the sailor and the vast freezing ocean. The implications for the Battle of the Atlantic were immediate and profound. U-boat attacks were peaking, and the loss of life among Allied merchant sailors and escort crews was crippling. The introduction of the Grumble suit would not stop the U-boat, but it would neutralize their deadliest auxiliary weapon, the cold. However, moving from a successful prototype to mass production and adoption was a bureaucratic and industrial nightmare. The Canadian team faced skepticism from Allied commands who were still fixated on the dry suit. McPherson and the Canadian Department of National Defense had to fight relentlessly to prove that their accidental discovery and its unconventional logic of controlled wetness could be the key to saving thousands of lives. The clock was ticking, measured by the sinking of every new torpedoed ship. Late 1943, early 1944, Allied naval commands London and Washington, D. The successful lab and tank tests of the Grumble suit in Canadian waters proved the science, but the rapid mass adoption faced formidable bureaucratic and logistical icebergs. The established naval authorities, steeped in decades of tradition, struggled to accept the counterintuitive logic of controlled wetness. The prevailing official standard mandated dry protection despite the repeated tragic failures of existing sealed suits. Dr. McPherson, now elevated to the role of a desperate advocate, found himself fighting technical skepticism and the entrenched inertia of Allied procurement systems. The British Admiral Tighe and the U.S. Navy had invested heavily in their own inferior dry suit prototypes, and admitting the superiority of a bulky, damp Canadian invention was a difficult political pill to swallow, particularly one born from an accidental discovery during a failed project. The reports state the men are wet. Dr. McPherson, an incredulous British officer, stated during a tense joint services meeting in London, "How can a wet suit possibly be an improvement? What means cold? Always has." McPherson patiently explained the thermodynamics. "Sir, it is not simply being wet. It is about eliminating convective heat loss. The thin stagnant layer of water warmed by the body acts as the primary insulator. Our materials, the tight wave wool in the external layers, prevent that heated layer from circulating and being replaced by the vast cold ocean." Despite the undeniable data, survival times exceeding all records, the initial orders were cautious and small. Production centered in Canada had to overcome challenges in scaling up the unique layered material construction required for the suit. They weren't just making a uniform. They were crafting a complex thermal survival system. Yet, The rising toll of the Battle of the Atlantic provided the stark immediate proof that crushed the bureaucratic resistance. Casualty reports arriving from the convoy routes were grim. While ships were being sunk less frequently due to improved escort tactics, when they were hit, the loss of life due to hypothermia was often near total. Merchant convoys reported entire crews dying in the water before rescue vessels could arrive. Sometimes just minutes later, the U-boat, though fewer in number, were still ruthlessly effective. Reports detailed the grim scene of rescue missions where sailors fully afloat in their standard cork life jackets were already dead from the cold. The need for a solution that extended survival from minutes to hours became a desperate strategic necessity for maintaining the flow of material to Britain. The turning point came when high-ranking naval medical officers traveling to Canada personally observed the rigorous testing and reviewed the pathological data. They finally grasped that the Grumble suit was not merely a new piece of gear. It was an entirely new technology that rewrote the rules of survival in cold water. Large-scale contracts were finally issued to Canadian and later American manufacturers. Production began in earnest, prioritizing the crews most at risk: escort sailors, rescue ships' crews, and critically airmen who might ditch in the sea. The Grumble suit, the accidental wet suit, began its slow, deliberate deployment onto the ships, battling the harsh North Atlantic environment. The life-saving invention, initially mocked by its own creator as a failure, was now being rushed into the hands of men who faced the certainty of a frigid death. Its ultimate test would come not in the lab, but in the chaos and freezing fury of a torpedoed ship. August 1944, the North Atlantic convoy HX 301 route. The ocean was a tumultuous, angry mess, whipped into white foam by a vicious summer squall. Aboard the Canadian corvette HMCS GOL, part of the escort group for convoy HX 301, the decks were awash with freezing spray. Below decks, the sailors were increasingly accustomed to the feel of the Grumble suits, now mandatory wear for anyone on watch or below the weather deck. The suits were bulky, making movement cumbersome, but the persistent warnings from command about the 5-minute survival window ensured compliance. Suddenly, the night erupted. A devastating spread of torpedoes from U-866 slammed into the heart of the convoy, hitting 2 large tankers almost simultaneously. The explosions were massive, lighting up the sky with burning fuel. Within minutes, the vast Black Sea was covered in burning oil and scattered debris, forcing the rescue ships and corvettes to maneuver through the terrifying inferno. Sub-Lieutenant Ali, now transferred to the G, watched in horror as a merchant sailor was tossed from the blazing deck of a tanker into the water. This was the classic scenario: massive shock, freezing water, and the near certainty of death before help could arrive. The Galt, avoiding the burning wreckage, was immediately ordered to search for survivors. The escort's priority was typically to hunt the U-boat, but the dire cold often made rescue secondary to the tactical fight. This time, however, the commander of the escort group, aware of the new suits, prioritized saving lives. The rescue ships picked up survivors from the first tanker quickly, but it was the crew of the second tanker, who had been in the water for nearly 40 minutes, clinging to wreckage, that provided the definitive proof of McPherson's invention. When the lifeboat crew reached the cluster of floating men, they fully expected to find frozen corpses barely held afloat by their life belts. Instead, they found something miraculous. The men, though exhausted and shivering violently, were conscious and responsive. They were able to grab ropes, climb ladders, and communicate their names and the location of others. They were alive, saved by the damp, ugly, life-extending suits they wore. One merchant sailor pulled onto the deck of the Galt, collapsed from exhaustion, but his core temperature was stable enough for immediate recovery. He was wearing the Grumble suit. The outer layers had become saturated, but the inner wool lining had trapped a warm, insulating barrier against his skin. His body had fought the cold for an impossible amount of time, and reports from HX 301 and subsequent convoys detailing the extended survival times quickly filtered back to Allied command. The data was unequivocal. The mortality rate for torpedoed sailors who successfully abandoned ship while wearing the Grumble suit dropped sharply. The suit provided the crucial golden hour of survival time. transforming a near-impossible rescue mission into a viable recovery operation. This success profoundly altered naval psychology. Sailors now faced the U-boat threat with a tangible hope of survival if their ship went down. The fear of the 5-minute death sentence, which was a psychological weapon for the Germans, was neutralized by a suit conceived in a Canadian physics lab. The accidental discovery of controlled wetness had been thoroughly tested in the worst conditions imaginable and proven to be the most effective, silent, life-saving device of the entire Atlantic campaign. It was an invention that turned the most hostile element on Earth, the freezing sea, from an executioner into a navigable obstacle. Late 1944, post-war era, Allied Naval Archives, and Global Rescue Services. By the final year of the war, the Grumble suit, also adopted and manufactured under various names by the British and Americans, was widely distributed among naval and air-sea rescue crews operating in the frigid waters of the North Atlantic and the Arctic. Its impact was not measured on a map showing territorial gains, but in the countless small human victories recorded in rescue reports. The cumulative effect of the suit on the Allied war effort was immense. By significantly reducing the mortality rate from ship sinkings, it maintained the vital flow of experienced sailors and airmen back into active duty. Every single sailor pulled alive from the freezing Atlantic represented not just a human life saved, but a trained professional returned to the Allied war machine. The medical and manpower costs that would have been incurred by the sheer weight of hypothermia casualties were drastically minimized. However, Dr. Clooney McPhersonin, the quiet Canadian professor from McGill, who turned his failed project into a life-saving breakthrough, received little public recognition during or immediately after the war. The immense secrecy surrounding the development and deployment of the suit to prevent the Axis from duplicating the technology kept the story largely hidden from the public consciousness. While the tank commanders and the fighter pilots received the visible medals, the true hero of cold water survival was an academic who dared to challenge the conventional wisdom that wet always meant cold. McPherson's simple, elegant solution, trapping a heated layer of water with layered insulation, was the foundation of nearly every cold water survival suit, immersion suit, and crucially, the modern neoprene wetsuit used globally today by divers and surfers. The legacy of the Grumble suit continues long after the U-boat were defeated. Its design principles became fundamental to all cold weather survival gear, saving thousands more lives in fishing, aviation, and search and rescue operations worldwide. The accidental discovery, the failure of the sealed dry suit became a technological foundation that permanently changed the relationship between humans and the planet's coldest waters. In the end, the most effective life-saving invention of the entire Battle of the Atlantic wasn't a powerful depth charge or an advanced radar system. It was a bulky, unconventional garment born from the rigorous curiosity of a Canadian professor and proven by the tenacious survival of sailors who defied the brutal logic of the North Atlantic. Emerging alive from the 5-minute death sentence, their survival remains a quiet, powerful testament to the triumph of ingenuity over the elements.